Alright guys, welcome back. We're going to be solving the question from the chapter 4 of engineering mechanics by Meriam, and we have a 250 Newton force that is applied to the foot operated air pump, and we have a return spring S that exerts a 3 Newton meter moment on member OBA. So we have a moment in this direction which is 3 Newton meter, and obviously this is going to turn this system in this direction when the foot is exerting the pressure at this point. It's trying to do the moment about this point. So the spring is obviously resisting that moment, so it has to be in the opposite direction, which is counterclockwise. So the question is asking us to determine the corresponding compression force C in the cylinder BD. So the cylinder by itself is in compression. The force that is applying from the cylinder to member O, AB is going to be in the opposite direction. So that's going to be our force C. And also we have the area of the cylinder, which is 45. We have the diameter of the piston in the cylinder, which is 45 millimeters. So based on that diameter, we can find the area, and that's why the question at the end is asking us estimate the air pressure generated for this condition. And we can state all of our assumptions. So first thing that is kind of like new in this question is that we are asked to find the pressure as opposed to force, and we know pressure is force over the area. And since we have the diameter, we have a cylinder, so the area would be pi divided by 4 times the diameter squared. So we should be able to find the area pretty easy since we have the diameter 45 millimeter, and based on that we can find the pressure. But before jumping on that, uh, we need to figure out this force C, which is the compression force in the piston, and after that we should be able to find the pressure from this formula pretty easy. So I'm gonna start with the free body diagram for the member OAB. I already showed the forces that we have. Like on top of that, obviously we have this 250 Newton force that is applying at A, and this one also makes 15 degrees here, and we can consider two forces at O. Since we have a plane OX, OY, let's just call our X and Y axis. And our first assumption in here is that we are in equilibrium, so our equilibrium equations are working in here. So we're going to have two force equation, one along x-axis, sum of all forces has to be 0 in x and y direction, and we're going to have one moment about any points that we want. So we're going to start with finding the moment about O, since we have the most unknowns at that point. And by doing that, the only unknown that we have is going to be this C. But since we want to use our 2D shortcut that we discussed over and over in this channel, we should be able to resolve these into two forces. And for doing that, we need an angle in here. Let's call it alpha. And finding that alpha is not that hard because basically we're going to have a right triangle in here, which is this right triangle. And this is going to be also the angle alpha. And all we need to do in here is just to find the tangent of alpha, which would be the opposite. And I'm just going to clean up the figure. So basically we know this distance here is 85. So that's a given in the question. All dimensions are in millimeter too. And from D to the bottom of here is 25. So if you just subtract this, we're going to get the opposite angle of this right triangle that I showed in here, this one. So 85 minus 25, so it's going to be 60, which is their opposite, and our adjacent would be basically this distance. This is also a given in the figure, so 225 It's going to be the distance from D to here, but we are interested in the distance from B, and we have one little 25 distance in here. So it's going to be 225 minus 25. So now we can find the angle alpha. So let's see what we get. So basically our alpha is tangent inverse of 60 divided by 200, which is going to give us 16.7 degrees. And now that we have this, we can resolve this force into two components. I'm just going to clean up the figure. It's very messy now. All right, so I tried to show the resolved force of C into two directions. So obviously the horizontal one, which is this one, is going to be C cosine of alpha, and the vertical one would be C. So this one is C sine of alpha. So let's go to our moment equation. Also we need to resolve this one as well. The 250 Newton force, the vertical one would be 250 cosine of 15, and the horizontal 250 sine of 15. Again, we are trying to find the x and y components of each of these two, because that way it's easy for us to find the vertical distance. So that's the whole point of resolving each of these forces. Otherwise, you have to find the vertical distance to the line of action, which is not that easy. So let's start with the 250 Newton first. So let's start with this component, the vertical one. So first of all, the moment is clockwise, so negative 250 cosine of 15 degrees, and the distance would be the distance from, actually the vertical distance from O to line of action, which is 125 plus 20. So 125 plus 25, which is going to be 150. We don't need to do unit conversion because it will cancel out at the end. We also have the moment of the horizontal component. This one also makes a clockwise moment. So another 250. This time we're going to have sine of 15 degrees. And this time we need this distance, which is 100 plus 85. So 185. And we're gonna have the moment of the force C. So this is going to be in this direction. The horizontal component is counterclockwise, so positive plus C cosine of the angle alpha, which was 16.7 degrees, and the distance would be, I'm just gonna clean up again. The distance would be this distance, which is 85. And also we have the moment of the vertical component. This one's also counterclockwise. So plus C, this time sine of 16.7 degrees. And the distance would be basically the distance from B to O, which is this 25 that we have in here. And this will be equal, I missed one more. We have this moment that we consider in here, 3 Newton meter. And one thing that I forgot to mention, that is that this is based on Newton meter, but what we did so far is Newton millimeter. So we can either multiply this by 1,000 to be consistent with the unit, or we can uh, divide each of these by 1,000. It's easier to do the multiplication in here. And yeah, that's pretty much everything for finding this C. So our C would be, so if you just factor everything and bring everything on the other side of the equation, so 250 cosine of 15 times 150 plus 250 sine of 15 degrees, 185 minus 3000 divided by 85 cosine of 16.7 plus 25 sine of 16.7. Let's just calculate this. So 250 cosine of 15. I'm just gonna put this in here. 250 times 185 times sine of 15 minus 3000 divided by 85 cosine of 16.7 plus 25 sine of. And yeah, our C is going to be 510.1 newtons. And this is not over again. We have to find the pressure. So our pressure in here would be the force, which is 510 divided by the area, pi divided by 4. The diameter in the question was 4 millimeter, 45 millimeter. So we have to divide by 1,000. So 45 divided by 1,000 squared, which is going to be in meters squared, and Newton per meter squared is going to be Pascal. Now let's just calculate this. So 510.1 divided by pi divided by 4 times 0.45 squared. And this is going to give us the pressure 32730.6 Pascal, and the final answer for this question. Hope everything was clear. Let me know if you guys have any questions. You guys take care. See you in the next video. Have a good one.